All right, welcome to part 2 of partial derivatives, where we actually do partial derivatives. Yay! Okay, so like I mentioned at the end of part 1, partial derivatives help us deal with variables that are a function of 2, or well, more variables. We're gonna start with 2 because that's the easiest. Also, it's actually representative of the physical world that we live in, because we live in 3 dimensions of space, and so a lot of times the rates of change that we're dealing with are going to be in 3 dimensions. So let's say that we have a 3-dimensional graph like this, where this is x, this is y, and this is z. Cool. So then I'm gonna do my best to draw some funky curvy shape like so. Woo! All right, so use your imagination. That's in 3D. Okay, so what partials allow us to do are to find the rates of change of z with respect to x and y. And the way that we do this is we start by holding one of the variables constant. So for example, if we were to hold x constant, we could carve out or take a slice of our object like so, and then we have this surface curve like that. So in this case, x equals constant. And then this curve that falls on the surface is only dependent on y. So you could say, in this case, z is some function of y only because x equals constant. Cool. Likewise, we could do the same thing for y. We could hold y constant, and then we cut a slice out of this shape, like so. Boop, 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 boop. Okay, and then in this case, y is constant. And this curve on the front is some function of x. So z equals, I don't know, k of... That's kind of a funky letter to choose, but that's fine. So, cool. So you can kind of think about it like if you had like a little apple or something and you sliced into the apple along the x and y planes, you would have different shapes of the curve on the outside of the apple. And that's what we are interested in. What does that curve look like and how much does it change? So, that's really what a partial is. So you could say that a partial derivative, let's do dx first. So there's kind of like an implicit understanding when we have our partial derivatives, which look like this. It's a curly d, or like a backwards 6. I think it's a Greek letter or something like that. But basically, when we have a partial of some function or variable z, with respect to x, the other variables, in this case we only have one, but if there were other variables, they would all be held constant. And likewise, dz, dy, we hold x constant. So then this is the rate of change of z with respect to x, where y is held constant. And this is the rate of change of z with respect to y, where x is held constant. We can also do second order derivatives, so d squared z, or actually let me back up a little bit. We can take the second derivative like this, which gives us d squared z dx squared, and we can do the same thing for y. So dy, partial of y of dz dy is d squared z dy squared. And we can also do mixed derivatives. Woohoo! So we could take the partial with respect to x of dz dy, and we would get d squared z dx dy. So then in this case, you are taking the partial of z with respect to y first, followed by the partial of that with respect to x. And if you're like, what? Don't worry, we're going to do an example. And then we could also do, can you see? Yeah, okay. We could also do this mixed partial, d dy of dz dx, and that would give us d squared z dy dx. Oftentimes these two are equal, but not always. So, okay, let's actually do an example. Because the best way to learn is to do. Haha! Same goes for mathematics. Okay, so let's say that we have some equation z equals x cubed y minus e to the xy. Okay, so first, that's fine. Okay, so first, yay, this is our equation. So first we're going to take dz dx. So we hold y constant. In other words, we treat y just like it was some random number. And then we take the derivative of z with respect to x. So if y was constant, it would kind of come along for the ride, and we would get 3x squared y minus e, whoopsies, got ahead of myself there. So the derivative of, well, I should say, d dx of e to the ax equals a e to the ax. So in this case, y is basically our a, so the y comes down, and we get e to the xy. Cool, okay, not so bad, right? Then we do the partial of z with respect to y. So in this case, we hold x constant, or we're like, x, you're just a number, you come along for the ride. So then we get x cubed minus x e to the xy. And now let's do those funky mixed partials that we looked at. So first, let's do d dx of dz dy, which is going to give us d squared z dx dy. And so we start from this equation, and we take the partial derivative of this equation, holding y constant. So what we're going to get is 3x squared minus, and then for this one we have to use the chain rule. So for this first part, if we say this is our variable, this is a constant, then we just get e to the xy. And then if we say this is our constant, this is our variable, we're going to get minus xy e to the xy. Cool. Okay, so now let's swap these and do the other mixed partial. So d dy of dz dx, and this is going to be d squared z dy dx. So in this case, we start from dz dx, this equation, and we hold y constant. Sorry, my bad. We hold x constant, and we take the derivative with respect to y. Okay, so if x is constant, then we're going to get 3x squared minus, same thing here, we do the chain rule. So minus e to the xy, and then minus, in this case, the x will come down, and we get minus xy times e to the xy. Oh, look at that! They are equal. That's funny, I drew a sideways smiley face. That's kind of cute. So these are equal. Yay! Interesting. This doesn't always happen, but it is good when it does. Okay, so let's try a couple of these second order partial differential partial derivatives. But I got my words mixed up. So let's say d squared z dx squared. So we start from this, and then we take the partial with respect to x. So we're like, y, you're still a constant. So then we get 6xy minus minus y squared e to the xy. And then lastly, let's do the partial, the second partial with respect to y. So d squared z dy squared equals, we start from this one. So this goes away because that's just a constant, my goodness. And then we end up with minus x squared e to the xy. Cool, not so bad. And we could keep going and doing these things. We could do the third partial derivative, the fourth, etc. And we could keep doing these mixed derivatives if we wanted to. So, quick word on notation. There are going to be different notations for the different subject that you're in. So I can't cover them all, and I don't want to cover them all. But a really quick mention is that you might see something like fxx or fxy. And what this is basically using this notation to say, okay, well, we're going to take the second order partial with respect to x. So the subscript variable is the partial derivative with respect to that variable. And then the number of variables in the subscript is going to be the order of that partial derivative. So in this case, they're both double or second order partial derivatives, d squared z dx dy, and then it goes in order. So if you saw f subscript x, that would be just dz dx. Cool. So that's something that you might see. You might also see like z subscript x, and that is the same thing. All right. So I hope that that was clear. Please let me know if you have any questions about partial derivatives, or if there are any specific partial derivatives that you're really struggling with. I'm happy to walk through those with you. But if you want to learn how to do partial derivatives, the best way to learn is to practice them. And once you do a bunch of these, you can handle them and no problem. So I would also recommend being able to check your solutions. So find a book that has solutions and then do them first without looking at the solution, and then check your answer to make sure you got it right. And if you didn't, that is okay. I can't tell you how many times I checked the solution when I was in college and was like, no! But then you just redo it and you try to understand the process so that way you can understand how you got your answer and how you either got it correct or didn't get it correct. And in all honesty, a lot of times the reason why I don't get the right answer is because I forget a minus sign. So now that I know that about myself, I can be like, okay, track the minus signs. We all have our own little quirks, and that's okay. We just have to understand what we're doing and why. Cool. Okay. So thank you very much for watching. Please let me know if you have any questions about other math topics and we can tackle them together. Yay! Go forth and math all the things. Woohoo! All right. I'll see you next time. Bye.